You know, what's the one thing that connects sending astronauts into space, the headlights on your car, and, get this, starting a fire with just sunlight? Well, the answer is this simple, elegant curve that's basically hiding in plain sight everywhere. Today, we're going to unlock the secret power of the parabola.
Right, so the parabola is definitely not just some abstract shape you had to memorize in a math textbook. It's actually a hidden key to some of humanity's greatest achievements. In fact, you probably interact with things designed with a parabola every single day and don't even realize it.
I mean, listen to this quote from the legendary NASA mathematician Katherine Johnson. Her job was to figure out the exact paths for missions like sending the first American into space. Talk about high stakes, right? Her calculations had to be absolutely perfect.
So how in the world did she pull off this kind of incredible precision, especially way back before supercomputers could just crunch the numbers for her? What was the secret tool that made it all possible?
Yep, it was the parabola. Her complete mastery of parabolic orbits is what allowed her to plot a course through the stars and, most importantly, bring those astronauts home safely. It turns out the simple, predictable path of this curve was the key to navigating the entire cosmos.
And this shape's usefulness isn't just for rocket science. It is literally everywhere. From the satellite dish on your roof, to the massive suspension bridges we drive across, to the telescopes we use to look at other galaxies. All of these things rely on the very unique properties of the parabola.
So what is it? What's the big secret that makes this one specific curve so incredibly versatile and powerful? Well, to figure that out, we've got to look at how it's actually defined in geometry. Okay, so the secret to the parabola's power isn't just that it looks like a U. No, it's buried in its very definition. A really precise geometric rule that gives it all these amazing properties. It all comes down to two key ingredients, a fixed point called the focus and a fixed line called the directrix. Now here's the magic part. Every single point on that curve is the exact same distance from the focus as it is from the directrix. That perfect balance is the secret sauce. It's what gives the parabola its almost magical ability to collect and focus energy. And this special relationship gives the parabola all its key features. You've got the vertex, which is that turnaround point right in the middle. Then there's the axis of symmetry, which slices the parabola into two perfect mirror images. These are the parts we can actually capture using equations.
So, let's take this cool geometric idea and translate it into the language of algebra. This is where we can really start to see how to use the parabola's power for actual design and calculation.
And to keep things simple, let's start with the most basic version, okay? We'll imagine a parabola whose vertex is sitting right at the origin of our graph. That's the point 0, 0.
From there, we get two standard equations. If the parabola opens up or down, the equation starts with x squared. If it opens left or right, it starts with y squared. It's kind of wild. Just by swapping x and y, you can flip the whole curve on its side. Now, in both of those equations, you probably noticed that little letter p. You're going to want to pay attention to that one. It is, without a doubt, the single most important variable here, because p is the bridge that connects the algebra of the equation to the actual physical shape of the parabola.
So what does p do? Well, it represents the distance from the vertex to that super important focus point. The sign of p also tells you which way the parabola opens. If you've got x squared and p is positive, it opens up. If p is negative, it opens down. It's basically the control knob for our curve.
But I mean, come on. In the real world, things are almost never perfectly centered, right? Satellite dishes and bridges aren't built at some mathematical origin. So how do we deal with that?
Well, the solution is actually pretty elegant. We just give our equation the ability to move. We can shift the parabola anywhere we want on a graph, left, right, up, or down, without changing its basic shape at all. To do that, we bring in two new letters, h and k. All we do is replace x with x minus h and y with y minus k. Just think of h as your horizontal shift and k as your vertical shift. This moves our vertex from that simple 0, 0 point to any new point we want, hk.
Let's look at a quick example here. In this equation, x minus 4 tells us that h equals 4. Easy enough. Now, y plus 8 is just another way of writing y minus negative 8. So that means k equals negative 8. And boom, just like that, our vertex isn't at the origin anymore. It's now at the point 4, negative 8. It's as simple as that.
Okay, time for the big payoff.
We've defined the parabola, we've figured out the equations. Now let's circle all the way back to the beginning and connect all this math to its incredible real-world power.
This right here, this is the magic trick. This is the secret. Any kind of energy, light, sound, radio signals, whatever, that comes in parallel to that axis of symmetry gets bounced and perfectly concentrated at one single point, the focus.
And there's no better example of this principle in action than a solar cooker, or in this case, a little pocket-sized fire starter. It's nothing more than a perfect parabolic mirror, designed to focus the sun's rays with pinpoint accuracy.
So let's say the design calls for the igniter, the little spot where you want the fire to start, to be exactly 1.7 inches from the bottom of the mirror. Well, that means our focus has to be at that exact spot. So our critical value, our P, is 1.7.
All right, now we can build the perfect fire starter using math. First, we grab our basic equation for an upward-facing parabola, x squared equals 4py. Second, we plug in our p-value of 1.7, which gives us x squared equals 6.8y. That's it. That's the formula for our perfect curve. Finally, to find how deep the dish needs to be, we use its width. It's 4.5 inches wide, so we look at a point 2.25 inches from the center. We pop 2.25 in for x and solve for y, and the math tells us the dish has to be about 0.74 inches deep. Any other shape, any other depth, and it just won't work.
So you see, the parabola is so much more than just a shape. It's a tool. It's a natural phenomenon for focusing energy that we can describe perfectly with math. Now that you know its secret, this perfect relationship between a point and a line, what could you design with it?